Okay, in this video we're going to investigate projectile motion. So it's the biomechanical principles of motion of an object, sometimes it's us, sometimes it's a ball, through air and also through water. The key principles we're going to investigate are lift force, so principles associated with projectile motion, so lift force, the Magnus effect, spin of an object, the height and the angle of release, and also the velocity of release, and the key skills remain the same throughout the biomechanics unit. So projectile motion, the definition of projectile motion is anything that's launched into the air, and the things that influence something that's launched into the air are gravity and also wind or air resistance. What we can do, a way of investigating projectiles, is to split it up into a vertical and a horizontal component, because they have different factors or forces which are influencing them. The vertical component is influenced by gravity. The horizontal component is influenced primarily by air resistance or wind resistance. There are three main things that affect the flight path of a projectile that we can control, and they include angle of projection, the speed or the velocity of projection, and the height of projection. So they're things that we control as the person throwing the projectile object or projecting ourselves as a projectile. Things in this table indicates just the variables that are influenced by those factors. So the flight time, how long the projectile is in the air for, is influenced by the initial vertical velocity or the speed of projection, and also the height of release. The horizontal distance is influenced by the horizontal velocity and height of release, and so on. One of those factors we've just discussed is the angle of projection. So that's the angle at which the object is released into the air. Okay? If something has a vertical trajectory, for example, if we project ourselves into the air in this volleyball spike or block, then the angle is 90 degrees. A common angle of projection in golf is around the 45-degree angle. And in cricket, a cricketer might want to throw the ball really quickly and hard at the stumps and keep it really low, so the angle of projection will be 0 degrees. So this is a different thing. It's applied in different sports depending on the requirements of the sport. This table here just indicates the projection speed, so the speed of release, and also the projection angle and how long a particular object might go. So if we have an object and we project it at 10 meters per second at an angle of 10 degrees, then it will travel about 3.5 meters. If we increase the projection angle, you can see that the range of that object is increased, and so on and so forth. When we get to 45 degrees, then we hit a maximum range for that projectile. And then as we continue to increase the degrees that we release the object, then the range decreases again. So it sort of works in a parabolic shape. If we increase the projection speed, then obviously that has a significant effect on the range. And again, if we hit that 45-degree angle, which is the optimal angle for a projectile, then we can get to the maximum point, the maximum range for that projectile. Speed of release is another factor that we can control in projectile motion, and that's generally how fast you throw the ball or the object or yourself into the air. And a useful way of calculating it is to split it into the vertical component and the horizontal component. So the vertical component will determine how high the object reaches and also will influence the flight time. And the horizontal component will determine how far horizontally that object will fly. So in this table here, we've got the effect of speed on the distance covered by a projectile released at 10, 20 and 30 meters per second from an angle of 45. So the angle of projection is the same. So you can see when we have a speed of release of 10 meters per second, then the object will travel about just over 10 meters. When we have increased that to 20 meters per second, then the object will go just over 40 meters, and if we increase the speed of release to 30 meters per second, you see there's a significant effect, and we can actually get the object to go about just over 90 meters, and the height of the object through the air increases as well. So you could think about that in terms of a javelin throw. If you throw the javelin harder, you impart more force into the javelin and therefore increase the speed of release. You would expect the javelin to travel further through the air. Another factor that influences a projectile is the height of release. In the examples on the right hand side here, if we've got a projection height of 0, so we might be hitting a golf ball off a tee on the ground or just straight off the ground, and the projection height is 0, then that object will travel in a nice curved parabolic path. If we project it at a height of 2 meters, for example, when you shoot a basketball, your projection height is going to be obviously 2 meters off the ground, and yet the ball might, if you miss it and you have an air ball, you might still hit the ground. So that will just influence the parabolic shape of the projectile. It still follows that nice curved shape, but it obviously starts from a much higher point. And this might be the example of a basketball shot when you are shooting from about 1.5 meters off the ground and shooting up towards a ring. This is probably particularly important in golf, where golfers have to hit off a tee, and they might be above the green, so they might be 10 or 15 meters above the green, or they might be below it, and that will influence the type of shot that they're going to play, because if they say hitting from higher above the green, then the projectile is going to go further, which means they might need to drop a club so that they don't overshoot the green. So when a ball or an object or ourselves moves through the air, we have two words that we use to describe that. The first one is laminar flow, and that's a flow of the air when the air is not disturbed a great deal. The air flows nice and smoothly and parallel around the object. When an object moves through the air and it disturbs or sometimes it can move through the water as well, and it disturbs the flow, then the layers next to the surface of the object get mixed together, and this becomes turbulent flow. So you might have heard, if you've ever been on a plane before, that the captain will say we're going to be experiencing some turbulence. That's when the flow of air around the plane is a little bit mixed around, and there's turbulence being created, so the plane might jump around a little bit. Another key factor in projectile motion is buoyancy. So that's how well you will float in water, and the buoyant force is the weight of the fluid displaced by an object. Swimmers will obviously need to consider their buoyancy, and quite often they'll wear swimsuits which increase their buoyancy. It's the material that the swimsuit is made up of, so that they can sit higher up in the water and they're not having as much drag when they're working through the water. We also use objects that are buoyant when, say, young children are swimming. So if you've got, say, a 1 or 2 year old and you want them to be able to swim but you don't want them to drown because they'll sink, you might give them floaties, and that increases their buoyancy so that they float to the top of the pool regardless of where they are. Coming back to that laminar and turbulent flow, we've got a force called a drag force, and this is generally any object that flies through the air will have a drag force. It's also known as air resistance, and when we're in water it's known as hydrodynamic resistance. Give you a minute to read through some of those. You can see the two different objects here have different properties of drag force. So this is the cyclist's helmet, and the cyclist's helmet is designed to try and cut through the air and reduce the turbulence out the back. The more it does that, the less drag that it puts on the cyclist, therefore the cyclist can ride quicker. A tennis ball, which is a perfect circle, doesn't cut through the air very well, so it increases the turbulence behind it, which drags it, and that means that the tennis ball slows down significantly as it travels through the air. Drag is affected by the following factors. So it's the shape of the object and how streamlined it is. So if you look again at the cyclist example, this rider has a one of those sort of bullet type helmets on, which streamlines the drag that's coming off the back of the helmet. Drag is also affected by the density of the fluid. So if we're travelling through air compared to water, that's going to increase the drag. And that's one of the reasons that we swim a lot slower than we run, because the density of water is significantly higher. So as we swim, there's a lot of drag to work through, whereas when we're in the air, there's not as much drag, so it's easier to run. The velocity of the object has a major influence on the drag force. For example, cyclists, when they are travelling up a mountain, they might only be going at 10 or 15 kilometres an hour. There's not a lot of wind resistance, air resistance there. So that tends to separate the men from the boys in the cycling. But then when they get onto the flat roads and they're travelling at 45 kilometres an hour plus, the drag is significantly increased. So quite often cyclists will sit behind one another, which reduces their own drag force. The area of the object in direction of the motion is also important. So if you've got a cyclist here and he had his hands up on the handlebars, he would be sitting up higher, which increases the cross-sectional area that's actually trying to cut into the air. So generally the cyclists will try and get down on their drops here, and they'll try and reduce that cross-sectional area cutting through the air so that they're not creating as much drag behind them. It's quite an interesting little factor there, which you can read and pause this video and read if you like. One of the final ones we're going to talk about is a lift force. So a lift force acts perpendicular to the flow of the fluid. It's affected by a number of different things, so the velocity of the fluid, density, size and shape, foil shape, etc. But a lift force is used when we look at planes. So planes create a lift force. They obviously have their engines which propel them forward, and then they'll use their wings to create a lift force which allows them to fly through the air. Another example you can see down here is the example of a plane's wing, and what it does, it generates an area of high pressure underneath and an area of lower pressure above the wing, and that creates a pattern of, or not pattern, a force of lifting the object from the areas of high pressure to the areas of low pressure. With a foil shape, the angle of attack is really important. So if we have a zero angle of attack, there's not going to be much lift force, if any. What will happen on the plane, if you see a plane during takeoff, the wings, the little bits on the wings which can extend out, will increase the angle of attack, and that allows the plane to take off. If that angle of attack is increased too much, then it creates too much turbulence behind the object, and that will actually decrease the lift force that is occurring. So this is really important in ski jumping, where the athletes have to try and get the optimal angle of attack to increase their lift force to allow them to jump further. And the Magnus effect, which is an effect which is really easy to see in table tennis when you spin a ball or an object through the air. So what we're doing in the Magnus effect is putting spin on a ball, which creates areas of high and low pressure. So as an object travels through the air, as it spins in a particular direction, one side of the ball which is going against the air is going to create lots of turbulence, and that increases the area of high pressure, and the other side of the ball is flowing nicely with the spin of the ball. So that means that we've got low pressure down here, and that ball will tend to curve or spin down, if you like, through the air, because things like to travel from areas of high pressure to areas of low pressure. In golf, another example of that is when we hit the golf ball, we are spinning it the other way, I suppose, into the wind. So again, that makes an area of low pressure above the ball as the air sort of flows nicely with the spin of the ball across the top. But down here, when the air is hitting it and also the ball is spinning, that's creating lots of turbulence, creating lots of high pressure as the wind has to be forced against the air that's sitting next to the ball, and that means that the ball will actually curve up and it will hang in the air for longer. Another good example of this is when you're playing table tennis and you want to put side spin on the ball. If you hit it with side spin, it will curve through the air, and that's the same thing with the Magnus effect, where we're applying spin to the ball, which creates these areas of high and low pressure so that the ball will curve. And an example is the soccer kick, Bend It Like Beckham. He wants to kick it into the goals, so he has to put side spin on the ball, which creates that that Magnus effect back here and allows the ball to curl from outside the goalpost into the corner of the net. Last one in this presentation is to do with surface differences. So in cricket, cricketers will often shine one side of the ball, and that allows for the surfaces of the ball to be very similar to the Magnus effect. So what happens is one side of the ball is rough and it's turbulent, and the other side of the ball is nice and shiny, and as it travels through the air it changes the pressure on either side. So one side gets a lot of pressure, high pressure, and the other one has low pressure, and so the object tends to move through the air with what we call swing. And that's the end of this presentation.